Imagine you ask an AI for a list of research papers on a highly specific topic. Within seconds, it generates a formatted response, complete with titles, authors, publication dates, and even direct links. But if you go looking for those papers, you will hit a dead end. The authors never wrote them. The journals never published them. The entire list is a fabrication, delivered with unwavering confidence. If a human invented facts like this in a professional setting, they would face immediate repercussions. We exist in a society where asserting false information carries heavy social and professional penalties. Through everyday interaction, we learn that saying "I don't know" is a survival mechanism. Admitting uncertainty protects us from the consequences of being confidently wrong. Artificial intelligence operates without these real-world stakes. Its understanding of successful behavior is shaped entirely by its performance on digital benchmarks and leaderboard rankings. These fabrications represent a mathematically optimized strategy designed for the specific digital environment the model was raised in. To understand why AI makes things up, we have to look past the surface-level errors and examine the underlying incentives of the testing environment itself. At their core, language models operate on a mechanic called next token prediction. They read your text, calculate the probabilities of the next word, and make a guess. This chart represents a model's training data. Most concepts are densely connected, but rare facts, like an obscure birth date or a specific dissertation title, appear as isolated points. The model has very little data to draw from, creating a statistical gap. When the model hits these gaps, it has to guess, and because every word is an independent probabilistic event, each guess carries a small chance of being wrong. Once the first guess is slightly off, that error influences every word that follows. The drift from the truth compounds exponentially, turning a tiny statistical error into a full-scale hallucination. At the pre-training level, this drift isn't an intentional choice. It is the mathematical result of microscopic errors accumulating over the course of a sentence. The math of pre-training is only the foundation. After the initial build, developers use behavioral training to refine the model, often relying on a system called binary scoring. These benchmarks grade the AI on a strict 0 to 1 scale. It is a digital version of a multiple-choice exam, where every answer is either completely right or completely wrong. This grading structure creates a specific incentive. If the model evaluates its own knowledge and chooses to abstain from an answer, its score is guaranteed to be 0. Look at the probability matrix for a 4-option question. If the model says "I don't know," it scores a 0. But by guessing, it maintains a 25% chance of securing a point. Reinforcement learning algorithms train the model to maximize its expected score, reinforcing a persistent test-taking behavior. The model learns that guessing is more profitable than admitting ignorance. It outwardly projects absolute confidence, even when its internal certainty is low, creating a disconnect between how sure the model sounds and how accurate it actually is. We have built an environment that punishes uncertainty. In this world, bluffing is the model's most rational strategy. Reducing hallucinations requires a total rewrite of the incentives that define AI success on the leaderboards. A new grading system would continue to award points for correct answers, but it would actively penalize incorrect guesses with negative points. The critical change is in how we value silence. By rewarding the choice to abstain, we provide a mathematical safe zone for uncertainty. The model is finally incentivized to be honest about what it doesn't know. You can apply this same logic to your own work. By setting a strict confidence threshold in your prompts, you tell the AI to only provide an answer if its internal probability exceeds a certain limit. Advancing the technology requires moving beyond simple generation and building systems that can accurately recognize the limits of their own data.